Let's look at the mathematical structure that we need to describe the situation. We're going to use matrices and vectors for a reason we'll see in a second. And so let's define the following structure. We'll define some 2 by 2 matrix, SI, where I can be the direction x, y, or z, acting on a spin up in that direction, gives us the value plus h bar over 2 spin up. So we want to find some matrix which has a normalized eigenvector whose eigenvalue is plus h bar over 2. And for the other option, we'd like the same operator acting on the other normalized eigenvector, spin down, gives us minus h bar over 2, because these are the only two possible options. We'd like these matrices to be Hermitian because we need the eigenvalues to be these two values here. They need to be real because things we measure in reality are real rather than complex. But also in this case, we know the full set of eigenvalues, they're h bar over 2 and minus h bar over 2. Since those are both real, we must have a Hermitian matrix. Okay, why do we choose matrices? Well, we require this to be the case. We need objects which tell us about the spins in the different directions that do not commute. If they commuted, remember if two matrices commute, we can find a simultaneous set of eigenvectors for them. But we can't have a simultaneous set of eigenvectors for these two operators, because if we could, then we could say what the spin in the x direction and what it is in the z direction at the same time. We'd have eigenvalues of both would be well defined at the same time. But we know this can't be the case because we can do this z, x, z measurement, for example, and the fact that so if we do repeated z's in a row, we'll always get consistent results. But if we do z, x, z, we could get the opposite result to what we got before. So if you think about it, this structure tells you that you must be using something which has the properties of non-commuting matrices. Whether it's those or something weirder is up to you, but this is the structure we've settled on. And in fact, there's another condition. It's not just that so you get a random value in the z direction if you've measured in the x direction before. Your probability of plus or minus a half is now 50%. So that additional structure actually tells us that what we're looking for has the following property. So the commutator of these two operators, remember the commutator of matrices A and B is AB minus BA, is how much they fail to commute with each other. The commutator of two of these spin operators should be IH bar times the other spin operator. And the sign here will depend on the order in which you do these. Okay, so we'll take a look at how this exact structure comes about in the problem sets. For now, we can identify a set of 3 2 by 2 matrices that have these properties, and they're as follows. So the h bar over 2 times these matrices sigma I, where these are the Pauli matrices, defined as follows. So there are 3 matrices defined like this. They're not the only matrices that will have these properties, but they're a particularly convenient choice for what we'd like to do. So in particular, let's take sigma z here. It's just 1, 0, 0, minus 1. And we can see that the normalized eigenvectors for that matrix must be this. So multiply sigma z by h bar over 2 to get sz, the spin operator in the z direction. And that is just h bar over 2 times that sigma z. So acting on this vector 1, 0 must return h bar over 2, 1, 0. So that's good. That's got the structure of our spin up. And sz acting on 0, 1 is minus h bar over 2, 0, 1. So that has the structure of our spin down. And you can check that your two eigenvectors for both of these matrices have the same properties. Okay, so let's just copy our z eigenvectors again. And the spin up value, in x eigenvector is as follows, which you can readily check from the matrix itself. And we can decompose this into spin up and spin down in z directions as follows. Because we can add 1, 0 and 0, 1 to get 1, 1 and multiply by the prefactor to normalize, and we get r up in x eigenvector. This, I didn't have to take this form, but we knew that we must be able to write, we can write any 2 by 2 complex vector in terms of our z eigenvectors, because these are the eigenvectors of a non-degenerate Hermitian matrix. And remember from a previous video that the full set of normalized eigenvectors of a non-degenerate Hermitian matrix must form a complete orthonormal basis. So we can expand any vector in that space in terms of a complete set of these, and there's only two of them in this case. Okay, so why do we want to do this? Well, say we've prepared a state in, say, up in X. We pass it through a Stern-Gerlach apparatus in the X direction. We select the beam that's spin polarized plus a half in units of h bar. But now we want to pass it through a Z apparatus and look at the results of what's coming out. So we want to schematically want to do this. So this is schematic for the Stern-Gerlach apparatus polarized in the Z direction, sorry, X direction. We pass some beam of electrons into here. We select out only the plus h bar over 2 results. The others we throw away, hit them into a screen. So everything now coming over here, and my beam is getting redirected through some magic, or you can put this in the right direction. Or you can use electric fields to redirect it, doesn't have to be magic. So we're going to take this set of electrons where their spin is known to be plus h bar over 2 in the X direction, and we pass it into a Stern-Gerlach apparatus in the Z direction, and we want to know what are the probabilities for getting h bar over 2 and minus h bar over 2. Well, we take our result here, up in X, we decompose it into the Z basis, so we have these results, and then the amplitude for finding up in Z is just given by the coefficient of up in Z. Okay, so we have this result. The amplitude for measuring up in Z for a state which is known to be up in X is given by the inner product up in Z acting on inner X. Acting on up in X. Okay, so we start from our initial state and we act what we want our final state to be, and that'll give us the amplitude. If we do that up here, we find we're going to act up in Z like this from the left. It comes through, let's not worry about this one. Acted on here, we get up in Z, let's rewrite it. So we get the inner product of up in Z with up in Z, but we know that must be 1. Up in Z with down in Z is 0, because again the basis is orthogonal, and so we just get the answer 1 over root 2. You could have done it by writing it out in this particular choice of basis, but you didn't need to. So that's the amplitude, but amplitudes are not what don't give us the probabilities. We use the Born rule. It's the modular square of the amplitude, and so we have the result, the modular square of the previous result. But this is actually a totally general statement that works for not just spin a half, not just finite dimensional Hilbert spaces. Throughout all of quantum mechanics, we can say the following. The amplitude for measuring a state psi final, given a state prepared as phi initial, is given by the inner product of psi final with phi initial. And the corresponding probability is given, as the Born rule tells us, by the modulus square, which can be written like this, where phi I, I've just abbreviated phi initial to phi I, psi final to psi f. I know it's very exciting, isn't it, Jeffrey? It's completely general, doesn't just apply to this particular case. Okay, so we'd like to perform repeated measurements, something of the following form. We'll send in a beam, we don't need to know what it is. We'll pass it through a Z Stern-Gerlach apparatus. We'll take only the plus h bar over 2 results, feed it into a Y apparatus. We'll take, let's say, the down results, put that into an X, and we'll take the up. This is all totally arbitrary. I'm just making sure I'm sticking to my notes, which will appear in the notes that you're getting handed to you. And finally, we'll put it back into another Z, but let's see the probability for it to come out down. How do we do this? Okay, well, let's start at this point. This is the first time we know the state of the particle, and we know here that it's up in Z. So what's the state here? Clearly, it must be state down in y, right? Because it's just come out of a y Stern-Gerlach apparatus. What's the amplitude for it to be in that state? Well, it was up in z, so we want the amplitude for it to be down in y, given that it was up in z. And we know that from the previous board, that's given by down in y, given it was initially up in z. Okay, so it's in this state. Remember, this is an inner product, so this is just a complex number, so this is our amplitude. So it's in this state, but this is the amplitude, because it was initially in this state, and it must finally be in this state. We can rewrite this slightly more neatly as follows. So again, this is the state, this is just an amplitude, but I pulled it over to the other side, so I get this nice outer product here. Okay, over here, it's going to be in the state up in x, but what's the amplitude for it being in that state? Well, this was the ingoing state, and that's the outgoing state, so we know that our amplitude is going to be as follows. So it's getting a bit complicated, but all it is this previous state here. This is the initial state as far as this is concerned. The final state is up in x. So we take inner product of final state with initial state, and that's our amplitude, and we multiply it by the state itself. So rewriting this slightly, we have, so I've just pulled the state through the amplitude again, just as before. You actually see what we're doing every time is just multiplying from the left by the outer product of the relevant measurement in each case. And so finally, we'd like to say, what's the amplitude for it to end up down in z? Well, that means that we're going to create the state down in z. So let's act from the left with down in z. Onto this, so it's up in x, down in y, and it started off as up in z. So the amplitude for it to end up in this state here is just given by this. Let's rewrite that. So it's a chain of conditional statements. The amplitude for down in z at the end, but this is conditional on the fact that it was up in x previously. That's conditional on it being down in y before that, and that's conditional on it being initially up in z. It's given by this amplitude here, which is just the amplitude of the state we just evaluated. And we happen to know that each of these different things, you can work it out using the matrices, or we can just use the fact that the probability for it being measured in any particular given state in z, given a certain state in x, and the same is true for any orthogonal measurement, the amplitude must be 1 over root 2, so the probability is at half. So we get the following, 1 over root 2 cubed, and so the probability is 1 over 2 cubed, which is 1 over 8. So we're going to use this kind of chain of reasoning when we take a look at a demonstration of this type of effect in a separate video.